So here we're looking at another example of exploring the features of a function using both the knowledge that we have from our training of pre-calculus and calculus skills, and also using the tools of technology. So again, I'm going to, for the beginning, just look at what features I can see before actually looking at the definition of the function itself. This is the default screen for Desmos, which has the x coordinates running from -10 to 10, and then the y coordinates running whatever the y coordinates are running, so that the x and y unit length is the same, and so that it fits in the window. So looking at this, it looks very much like I have an odd function that is periodic. I could probably guess the period. It looks a little bit like it might be kind of a pi, or I guess 2 pi. And something that I could do quickly is I can ask Desmos to step by increments of pi, and it does very much look like a period of 2 pi. So I'm going to go ahead and leave that there. It looks like I have some max values around 1. And it looks like wonderful. Since I wonder if this is true, since if it's only giving me those values since I changed the x step. Oh, no, it is giving me these pi over 2, pi over 3 values. So Desmos does a lot for us in this case. So here we have, and I'm actually going to ask Desmos to step by pi over 6, because that gives me my pi over 2s and my pi over 3s. Of course, it's going to ignore me if I'm zoomed out too far. But this is kind of nice. So it looks like I have local minimums at, I don't know what that is in terms of pi. Looks like it's a little bit bigger than pi over 6. But here we have a local minimum at pi over 3, a local max at pi over 2. So there's a lot that Desmos actually gives us just in the picture. And let's actually dive into the function. So here's what it is. It's sine of the quantity x plus sine of 2x. So composing sine within a sine, which is interesting. In terms of domain, the function, the graph, looks like it has a domain of all real numbers. And sure enough, all of the functions here don't have any restricted domain. Sine has a domain of all real numbers. And, I can add any number to another real number, and then I can put any number into this sine function. So it's going to be all real numbers. In terms of the range, it does look like my maximum value is 1 and my minimum value is -1. So I'm going to still put a question mark just to double check this, but I'm going to say it looks like it's from -1 to 1, including those boundary points. Symmetry and periodicity. So we did notice that it looks like it's odd. It looks like it is periodic with period 2 pi. So let's check the oddness. So if I look at f of -x, that should give me the same thing as f of x. Sorry, negative of f of x, if it really is odd. So let's see what happens if I plug in f4 of -x. And I can actually do this f4 of -x. I can see this graphically. This is what f4 of -x looks like. What this is doing is it's reflecting it across the y-axis. So reflecting it horizontally across the y-axis. And it looks very much like the same as reflecting it across the y-axis, across the x-axis. So this is reflecting across the x values, which is going across the y-axis. And this is reflecting the y values, which goes across the x-axis. So it looks like very much like it's the same, but let's actually plug this in and do this algebraically. Sine of negative x plus sine of 2 times negative x. So that's what f of negative x is. And I'm just going to put some dot there so it doesn't do any calculations with that. Now, sine of negative, so this is the same as sine of negative 2x. Okay, 2 times negative x is negative 2x. And this is sine of a negative of something. Since sine is odd, I can change that to the negative of the sine of 2x. Okay. And I see a negative in both of these terms, so factoring out that negative, this is the negative of x plus sine of 2x. And now I have sine of negative something, since sine is an odd function, I can say this is the negative of that sine of something. So let me just go back and this is filling in. And this is simplifying 2 times negative x equals negative 2x. And going from here to here, since sine is odd, that negative comes out. And this is factoring out minus. And this is, again, since sine is odd. Okay. So all of this says f of negative x is the same. Okay, so let me just confirm this, that this is the same as the negative of f4 of x. Okay, so therefore we have this function is an odd function. Let's check periodicity with period 2 pi. Like, we don't need to check that there's any periodicity less than 2 pi because we could just see on the graph, but let's double check that this is really a 2 pi periodicity. So f4 of x plus 2 pi. Well, so looking at the graph of that, it does look like it lays exactly on the graph of y equals f4 of x. That's great. So now I'm going to do the actual calculations. And here is f4 of x. Copy and paste. And then I'm going to do plus 2 pi. Plus 2 pi. Okay. Okay. And this is, so since sine is periodic with 2 pi, with period 2 pi, that means that the sine of something plus 2 pi is the same as that sine of that something. So this is, those are the same, since basically this is since sine is periodic. with period 2 pi. Okay, and then again, basically I can see this I'm going to leave that there. I'm going to rewrite this, put that plus 2 pi here, and now I see a sine of something plus 2 pi, and that is going to be the same as just that sine of something, since this sine is periodic. And this, I want to say, just, you know, rearranging the sum with at the end. Okay, so this is basically my justification to show that, okay, so now this is, this shows that f4 of x plus 2 pi is the same as just f4 plus of x. So that does show a periodicity with period 2 pi. Super. Okay. Intercepts. 0, pi, 2 pi. I mean, yeah. Let's actually, I'm gonna go ahead and take that. Oh, I've already done it in Wolfram Alpha. So this is actually interesting. If I ask for Wolfram Alpha for roots of this function, so keep in mind, this function has infinite roots, right? There's an infinite number of times where it crosses the x-axis because it's periodic. And so this response is a little bit baffling to me. It surprises me. It suggests a little bit that maybe there's only 2 roots to this function, and I wouldn't, like, if I was going to name only 2 roots, I would not name those 2 roots. And so and it shows negative pi and 0 and pi. And so it basically shows these 3 roots, but it looks like this is 2 pi, 3 pi. That looks like 4 pi. But I don't know why they chose 4 pi and negative 15 pi as the ones that highlighted it highlighted. There's some interesting programming happening behind there. But I think, yeah. So, I mean, we certainly can check that f4 of 0 is 0, and also of pi is 0, and also of 2 pi is 0. So it looks like all the intercepts are at all integer multiples of pi. So I'm going to say 2 pi n 0, where n is any integer. And it is not multiples of 2 pi, it is multiples of pi, all integer multiples of pi. I like to put n first, 2n times pi. I can plot those n pi 0, and instead of adding a slider, I'm going to just put in a bracket, a list from, I don't know, -5 to 5. ... Okay, so that's -5, -4, -3, all the way up to 5. So it's plotting all of them from -5 to 5, and it's, you know, there's a lot more of them. This is just me grabbing a few of the visible ones. Okay. We could label those or not. Limits at the edges of the domain. There's no such thing as the edges of the domain. End behavior. You know, this is a periodic function, and pretty much any periodic function, if you're not going to have any end behavior. So the limits at infinity do not exist. This is basically, there's no one value that the function is approaching for large values of x. For large values of x, you know, it continues to oscillate in this periodic way, you know, going back and forth between -1 and 1. Okay, intervals of increasing and decreasing. This is where we need to get a derivative in here. Let's go ahead and try just looking at the derivative as Desmos graphs it. This is pretty interesting. Okay. Looking at this. So if we look at where the, oh, look, here's the intercepts. Okay, so this is where the derivative switches between positive and negative. And I want to grab that derivative, and I can certainly calculate the derivative of this function using the chain rule. Looks like 2 applications of chain rule, but I'm going to get Wolfram Alpha to help me out. I'm just going to do d over dx of that function. And it looks like 2 cosine, let me take that in plain text. Copy to clipboard, and 2 cosine of 2x plus 1. Let's take that down here. And I don't want all of this stuff which says this is d over dx of that stuff. So this lines up exactly with what Desmos calculates as the derivative. So this tells me I have really two factors here. There's one where I have 2 cosine 2x plus 1, and then I also have one where it's cosine of x plus sine of 2x. That feels a little bit tricky, but I want to grab roots of that thing. See how, and this is pretty easy to get a hold of. So this is basically saying cosine of 2x has to be -1/2. But let's go ahead and take this to Wolfram Alpha. Roots of that function. So pi times n minus 1/3 and pi times n plus 1/3. So that's the same as like pi over 3 plus integer multiples of pi and negative pi over 3 plus integer multiples of pi. So, where was I? F4 prime equals 0, where x equals pi over 3 plus n pi, and where x equals negative pi over 3 plus n pi. Okay. So here's the pi over 3, and then 4 pi over 3. So those are happening every pi over 3 units. That is also, where is that? Subtracting a multiple of, it'll be this one here, negative 2 pi over 3. Subtracting 1 pi. And then there's also negative pi over 3 plus multiples of pi. So negative pi over 3, negative pi over 3 plus pi is 2 pi over 3, and then another one is 5 pi over 3. So here's, you know, there's several examples. Then let's look at the roots of this little monster. I'm going to put that in here, roots of that stuff. See what Wolfram alpha would give to us. Ooh. Okay, Wolfram alpha is not giving us any exact values. It's really giving us approximate values with decimal approximations. So, you know, I want to actually, since this function is periodic with period 2 pi, I want to go ahead and just restrict us to just looking at, 2 pi, one period of this function. Okay. So that, and then everything else is going to repeat. Okay. And so in that case, what we have is in one pi over 3, sorry, in one period, we have the pi over 3 and the 4 pi over 3. We have the 2 pi over 3 and the 5 pi over 3. And the other ones are, let's grab the roots that are between 0 and 2 pi. It looks like, yeah, it looks like I want a few more of those. And let's say if we can go from 0 less than or equal to x less than or equal to 2 pi. Let's see what Wolfram alpha will do with that. What if I put a comma here? It's not accepting that as a domain. Okay. Roots of, I don't know what that is. Okay, so let's, somehow it's taking roots and making a root. So let's, I want equals 0. Okay, solutions to this equation equals 0, where x is between 0 and 2 pi. Okay. There we go. Here's our solutions. And they're all real solutions. Interesting. Okay, so this also gives us those pieces. So x is approximately, so basically I think for me, what this is confirming is that I can just use this, this desmos graph that says, you know, it gives me these fraction multiples of pi, but then I can just say, well, and then the decimal approximations are as good as we get. Okay, so we have, you know, at this place where x equals 0.623, then the derivative, let me just highlight that, the derivative switches from positive to negative. That means here on the original function, the function is switching from increasing to decreasing. So we have a relative maximum there. So let's just now, like, don't worry about that Wolfram alpha. That just gives us a confirmation of what we are seeing in this graph, that there's nothing more exciting about these numbers. Local, and so we can see that the function is increasing on from in the interval from 0 to, and actually, you know, I can go okay, so on the interval from 0 to 0.623, and then it's decreasing on the interval from 0.623 to, that was a pi over 3. And then increasing on the interval from pi over 3 to increasing pi over 3, that's pi over 2, right? To pi over 2. Pi over 2. And then decreasing on the interval from pi over 2 to, that's 2 pi over 3. And then increasing on the interval from 2 pi over 3 to, what is this number? So 2 pi over 3 to 2.519. And then we can talk about the function is decreasing on the interval from 2.519 to, what is this number? 3.765. Okay, and I'm not going to finish this because I don't think it's necessarily all that interesting, but we can see, you know, that's where, this is where we have the increase and decrease. Global maximum and minimum. So I mean, I really, honestly, I think that there's 1, 2, 3 that we can kind of see, and then there's the symmetries of those. So there's, at x equals, what one is this one? This is the 0.623. So f4 of 0.623. And let's get a little bit, 623049. Okay, that's enough so that Desmos's rounding goes to 1. And then we have f of pi over 3. f4 of pi over 3. There's a relative minimum, and then pi over 2. Okay, so we can, these are really the only numbers that we'll see. So we have local, and this is going to actually give us the absolute maximum is 1, which occurs at x equals pi over, sorry, that's the 0.623049 pi over 2. And you might notice that this hump here is basically pi minus that number. So I could say pi minus 0.623049. And then I can go, well, pi plus that number, 0.623049. Oh, wait, those are the absolute maximums. So there we go. And my absolute minimum is going to be -1, which is going to happen at x equals pi plus that number. And then this is going to be 3 pi over 2, right? 3 pi over 2. And then this is going to be 2 pi minus that number, because this distance here is that same 0.623 distance. And then, so those are all absolute maximum and absolute minimums, and also local maximum and minimums. And we have some, let's see, local minimum value is going to be 0.94194 at x equals, and I believe that this is going to be the same number at x equals 2 pi over 3 because of there's so much symmetry here. At x equals pi over 3 and 2 pi over 3. And then flipping those are going to be at local maximums on the other side of pi. So local maximum is going to be negative. It's the negative of that same y value, negative 0.942. At x equals, this is going to be 4 pi over 3 and 5 pi over 3. Okay. And basically, you know, I'm doing this for x between 0 and 2 pi. You could just add 2 pi, you know, plus any multiple of 2 pi to all of these, and that you'll get all of them. Intervals of concave up and down. Let's take this. That's That's our first derivative. Let's look at our second derivative. All right. Ooh, yikes. And let's see, we have not very nice numbers for the intercepts of that second derivative. Let's go back here and take the second derivative. I'm just going to do d over dx of d over dx of that. So the derivative of the derivative. Looks like kind of a mess. Alternate forms, expanded form. Okay, it doesn't give us any zeros. Let's go ahead and take this plain text. And I'm going to look at where this equals 0. And I'm going to take away all of the equals so that where that stuff equals 0 from x going from 0 to 2 pi. And let's just see if Wolfram alpha has any nice multiples of pi, fraction multiples of pi that tell us where those numbers are. Yeah, nope. It doesn't give us any better numbers than what desmos is giving us. So we can basically take desmos and say, here are the points, those are the x values of our points of inflection. Okay, so we can see the second derivative is negative for x between 0 and 0.796, so that means the function is concave down. And then between x equals 0.796 and 1.301. It's hard to tell which label, which label goes with what. So here's 0 and then 0.796 and then 1.301. Between 0.796 and 1.301, we have the second derivative is positive, so the function is concave up. Okay, and then I think we have one more, and so all three of these basically, we just need these two values, and we can subtract them from pi or add them to pi or subtract them from 2 pi to get all of the rest of those numbers. So 0.796 and 1.301. Did I get those right? 0.796 and 1.301. Okay, so I'm just going to put in the points of inflection here. So there's 0, 0, 0 is a point of inflection. And 0.796 and f4 of 0.796. That is a point of inflection. And 1.301 with f4 of 1.301. That is a point of inflection. And then the next one would be this one here is kind of the analog of this, so it's pi minus 1.301. So pi minus 1.301 minus not divided by 1.301 and f4 of that number. And then here we have this point here is going to be the analog of that point, so it's going to be pi minus, that is pi minus 0.796. Okay, and then there's going to be pi 0 is, you know, this is another place where the second derivative switches from negative to positive, so that is going to be a point of inflection. The function is switching from being concave down to concave up, and then we can fill in the rest of the points of inflection basically by taking these and, you know, taking them pi plus these two numbers, and 2 pi minus those two numbers is going to be the rest of those points of inflection. So there we go. There's basically a full analysis of this function. We did actually, with our work on finding the local maximum and mins, we did actually confirm that this is, the range is from -1 to 1. Okay.